guys, and welcome to your notes for section 10-2. We are going to introduce conic sections today, and our focus is primarily on parabolas. So at the very beginning, your book's going to introduce, and you might want to go ahead and sort of breeze through it because we won't spend a lot of time here, but they introduce sort of this idea of what a conic section is. Conic sections come from this shape, or this three-dimensional solid called a double-napped cone, and they talk specifically about the intersection of a plane with a double-napped cone. So there are several options for really. If you had a plane, imagine you took like a piece of paper or a knife and you sliced through the double-napped cone. If you hit it at an angle such that you only went through one of the two cones, you'd cut a parabola. That's our focus today. If your plane were parallel to that base of the double nap cone, you'd create a circle. If it went through one of them, but sort of went at an angle there, right, then you would create the ellipse. And if you were sort of vertically aligned so that you were cutting through both double napped cones at the same time, you would create what's called a hyperbola. There are several ways to talk about these, but our book talks about each of these shapes as a locus or a collection of points. And so you'll see that in the way that we define parabola. We won't define parabola, for example, as a quadratic function. We will talk about it as a set of points with a certain geometric relationship. So that is our goal today. And my understanding is that in Algebra 2, you guys cover parabolas and you cover ellipses. So we'll probably spend or move a little faster on those two topics than we will on hyperbolas, which I don't think you guys have seen before. So the locus definition for a parabola is that a parabola is the set of all points in a plane that are equidistant from a fixed line. We call this fixed line the directrix, and a fixed point, which we call the focus. So we're going to fill that in here. So this gives us sort of this geometric version of what a parabola would look like. Let's draw a picture before we talk about our standard forms. So I'm going to sketch in the xy plane, our normal xy plane from Algebra 1. And we want to consider this line and this focus first. So when I go to sketch in my directrix, I can choose that to be any horizontal or vertical line. I have to make a choice here to draw one, but it could be any horizontal or vertical line. I'm going to make my directrix right about here, and I'm going to have my parabola centered at the origin because that's sort of our simplest version. But this line here represents my directrix. And my focus could be any coordinate point then that is on either side of this line. I wouldn't want to put it on the directrix. That wouldn't be very interesting. And for my picture here, I'm going to have my vertex centered at the origin. So I'm going to try to draw it so that I have exactly the same space here on this side from the origin as I do over here. I want those two values to be equal. And this coordinate right here will be my focus. In fact, let's go ahead and we'll write focus. The focus is a point, the directrix is a line. And they're evenly spaced, so that this length here and this length here, we're going to call that with a lowercase letter p, that those two lengths are equal. Okay. In this case, it's centered at the origin, but you could move this anywhere in the plane, but those distances would always be the same. What happens is that we want to imagine that we're sort of testing values everywhere. We want to pick only points, only coordinates, so that the length from that point, if I were to measure it perpendicular to the directrix and then straight to my focus, that I would get the same exact value every single time. And so let's draw in sort of what we know as a parabola. In this case, I can actually go right and left in addition to up and down. That's not true when you're talking about quadratics. And this definition is stating that if I were to measure the length, I don't think I did a great job sketching it, but if I were to measure this length right here and the length, right, creating that perpendicular to the directrix, and the segment that goes straight from my coordinate to the focus, that those two lengths would be exactly the same. And that would be true for any point that I picked, regardless of where on the parabola that it was. We're going to call this point right here V for vertex. Again, it would fit the definition. The length from the vertex to the directrix is identical to the length from the vertex to the focus. That's how we define our parabola. And then there's another special point that we want to talk about. This is sort of going to measure our opening of our parabola. And that would be creating a perpendicular segment to our directrix. It's going to give us a chance to measure that value. And I want to think about the length from here to here. That I can compute. That would be 2p. And therefore, this would also be 2p up and down, because the distance from the point to the directrix, right, that would be p plus p, if you look at down below, would be the same going from the point to the focus. The standard form of our parabola, when I write it in this conic form, looks a little different. We talk about x minus h quantity squared, so h being the x coordinate of my vertex, is equal to 4p and then y minus k, where k is the y coordinate of my vertex once again. P here is representative of that distance between the vertex and the focus, or the vertex and the directrix. They're the same value. Now, there's a second version to this. This is going to have an opening that either goes up or down. And I can tell because this formatting, although it looks a little different with the 4p, this formatting still looks like what I would normally think of as a quadratic function. I have a y equals, and I have an x coordinate that's being squared. So this version actually can't look like what I have drawn in over here. This version is either going to open up or it's going to open down. And the way that I know the direction is based on that p-value. If your p-value is greater than 0, then that means that you would be opening up. And if your p-value was less than 0, you would be opening down. I'm just a little bit short on the page. There we go. The alternate version of this has these two terms flip-flopped. You can also take y minus k quantity squared and set that equal to, again, 4p, but x minus h. And so in this case, I have the equation x equals y squared. This is not what I would normally consider as a quadratic, but it will graph. It would actually graph just like the one I have over here, where you're either moving to the right or you're opening to the left. And think about it this way, here you're opening upwards. So p greater than 0, that parabola is kind of swallowing the positive y-axis, whereas if p is negative, you're opening down and it's swallowing the negative y-axis. So to remember these two, when your p is positive, you are opening to the right. You're opening so that the parabola is sort of swallowing right on the inside here. If you think of it like a Pac-Man mouth, it's swallowing up the positive x-axis. When p is negative, it's opening to the left, it's swallowing the negative x-axis. And so that is my general form. Right here, we could actually, for this particular parabola, we could be even more specific because my vertex is at 0, 0. So it would look like 4px equal to y squared. This other piece that I drew in, the 2p, has a name. It's one of my favorite / least favorite vocab terms in math. The line segments through the focus with endpoints on the parabola and we say that it is perpendicular. I'm going to use the symbol for perpendicular from your geometry class. It's shorter. To the axis of symmetry, right? We could imagine drawing the axis of symmetry right through the center. To the axis of symmetry is called the lattice rectum. So there's a special name for that segment that sort of defines your opening for the parabola, and that is the lattice rectum. When you graph, you want to make sure you include the vertex. You would want to plot the directrix and the focus, and you would want to plot 2 additional points. That's not any different from your normal parabolas. And you would plot the 2 points on the edges of the lattice rectum so that you would get sort of this defined opening. How wide is it or how skinny is it? I usually just memorize this. And I know that this form will work then, and I have these sort of p values greater than less than memorized. If you would like to, if you know the vocabulary for directrix and focus and you understand the even sort of symmetry here, you could really just use this box to remember everything that you need to know about your parabolas. I did cut and paste from your book. They go into a lot more detail and create a lot of formulas. The problem is that it's a heck of a lot of stuff to memorize. So you're welcome to look through this. If you notice, they have the exact same values that I had down here, but they have just sort of spelled it out for every possible direction that you can point. In my mind, that's a little more confusing, but if you are, really loving to memorize things, go for it. I did a couple examples with you, and sometimes they'll give you in the textbook really nice ones that are already written out in that perfect form, and other times they're going to give you one that is just waiting for you to create that standard form for the parabola. And this is one of those. So I didn't stick with the easy ones. The homework will start with some simpler ones first, but I figured you've seen them before. We just reviewed when we did the spheres in chapter 11, we reviewed completing the square, which we also did in chapter 2. I know I have it in my notes in both places, 11:1 and in chapter 2:1, I believe. But we want to be able to complete the square to create that standard form. Now, this one's pretty nice, right? Because it's already got the quarter pulled out. And I do know a little something about this function, right? It's going to be a parabola. It's y equals x squared. It's going to be a parabola that opens upwards, right? I can tell just by looking at it with the positive value here and the positive x squared. My goal, remember that form we just put on our front side, my goal is to write it as 4p times y minus k, right? There's my y equals. And then I need my x minus h quantity squared. So that's where I want to get to. The coefficient, now this trips people up. Normally in chapter 2 when we did parabolas, we wanted it on the x squared, but actually we want the extra coefficient over here on the y side, and we want a 1 in front of our x squared. So I'm going to go ahead, and the first thing I'm going to do is write it as 4y, multiply both sides of my equation by 4, equal to x squared minus 2x plus 5. And notice also that I want to be subtracting. I need a perfect square over here, and I'm going to have to create sort of the k value on the other side. So I rewrote mine as 4y minus 5 equal to x squared minus 2x. And then over here, I want to go ahead and complete the square. So we just reviewed this. You take your m, your middle term's coefficient, and divide it by 2, and then you add it in as a square. So half of negative 2, I'm going to add in a negative 1 quantity squared. Now remember what we talked about. Now we have messed up the equality of this equation. If I were to multiply it out, I would no longer have the same thing that I started with. So because I added in blue on the right-hand side, I also need to make sure I have a net gain of 0. So if I've added 1 on the right-hand side, I also have to add 1 on the left-hand side so that I maintain that equality. So that means that I can write this as 4y minus 4 equal to, and then over here I'll go ahead and factor x minus 1 quantity squared. And recall, I want it to say y minus k, right? I need a coefficient out front, so I'm going to pull the 4 and as GCF, and now I have it written in that standard form. If that's the case, then let's think back to sort of our goal again, right? I'm going to write it down here below so that I have it to compare with. Oh, almost forgot my square. Right? Think about if we have these two things aligned, what can we do from our equation, right? I can see that 4p, right, should be equal to 4 or p equal to 1. And I can also read off my h and my k, right? X comma y, that vertex would be at 1, 1. And that's going to give me what I need to figure out a nice picture here. Let's start with our vertex. I'm going to zoom in a little bit because I know where this one's going. My vertex is at the coordinate 1, 1. We'll put a V here for vertex. And then think about that image, right? I'm going to go ahead and I'm going to count a p-value. Now remember, I want it to be opening upward, and the directrix lives below the axis, or sorry, below the parabola itself. So I'm going to count down 1 unit, and I'm going to also count up 1 unit from my vertex. And that will give me the locations for my directrix. I know that the directrix is below, again, because I know the parabola is opening upwards. So my directrix is at y equals 0. And I know then that my focus, which should be inside of my parabola, my focus is at the coordinate, let's see, I would go over 1 and I would go up 2. So 1, 2. If I have a decent sketch, I can just kind of count it out. So that gives me sort of some of the important points. I need to know sort of how wide this is. And what did we say about that lattice rectum? Well, we are going to count over 2p right and left from our focus. So I'm going to count 1, 2 units to the right, and that would take me to a coordinate on my graph. If I counted 2 to the right, I started at 1, and I'm moving right, so I'm affecting the x. I would be at 3, 2. It needs to be aligned with the focus, so the height will still be 2, but I'll have moved over 2 units to the right, and then I'll move 2 units to the left. So if I'm already at 1, moving over 2 units, I'd be subtracting 2, so this would be at -1, and then at the same height. And so my graph is going to look like this. Let's see if I can get a good sketch in here. There we go. And there's my parabola. You want to make sure that you include the vertex. You want to make sure that you include the directrix, the focus, and then the 2 endpoints on the lattice rectum that allow you to draw it in with some shape. So there you go. You have a nice example now of how to go ahead and graph a parabola that wasn't in standard form. Okay. The directions are going to say to use completing the square to graph it as a conic. So you can't just go back to your chapter 2 knowledge. You have to be able to do it with this method. Let's see. The other thing that you want to do, other than graphing, right? If I give you an equation, you should be able to graph. But you also want to be able to take some information and come up with the equation. So here we've got a vertex and a focus. One thing that I have found really helps is to make a quick sketch. Now, the thing is, kids really kind of drag their feet on this one. It doesn't say I have to draw a picture. And I don't want you to make a good, detailed graph. I just want you to think about the sketch that would come from this. The vertex is at -1 and up 2. So that would put my vertex here. My focus is at -1 and 0. Why do I want to do this? I want to think about the shape of the graph. I need to decide, does it open up or down, right or left? And if you think about it, the vertex needs to sort of the parabola is going to open up so that the focus lives inside of the bowl of the parabola. So I don't want to graph it going up because the focus would be underneath it then. I don't want to graph it going to the right. The focus would be outside. I know that this one, based on the information, is going to have a opening that goes down. So that tells me sort of which one to pick, right? If it's up or down, then it's y equals x squared. So I would have x minus h quantity squared equal to 4 times p, and then y minus k. So that little bit of a sketch can help guide my selection of which of the 4 forms that I'm going to have. It also tells me, since I'm opening down, that my p-value should be a negative number. So the vertex is kind of easy because they gave it to us, right? So we've got x plus 1 quantity squared, and we've got y minus 2. The only thing left is to figure out the p-value. P, recall, is the distance between the vertex and the focus or the vertex and the directrix. So here I have that value, right? I can think of drawing that segment right here, and I can just count if I made a little sketch, right? It's 2 units difference. So that makes my p-value equal to 2. It's actually not 2, it's -2 because I know that this parabola opens upside down, and so I want to put a -8 right here. And don't multiply it through, leave it in that standard form so that the person who picked it up could create a nice quick sketch. There's lots of variations on example 2 here. I gave you one more. Probably could have stopped there and not had a staple, but I gave you one more. And make sure you work through the homework because there's lots of variables in terms of how they can start you with this question. So you want to try a few so that you're ready to go. The next one really is no different. It just has a different set of given information. Here, notice they didn't give me the vertex, so I don't have that to start with, but they did tell me about the focus. So we're focused at the focus is at the origin, and the directrix is at y equals 8. So let's recall y equals 1, 2, 3, 4, 5, 6, 7, 8. That means I'm always at a height of 8. So I have a nice horizontal line. This is y equals 8. Okay, so we have to decide first thing, are we opening up, down, left, or right? And recall that the directrix should be sort of floating outside the parabola. The focus is on the inside. So for example, I can't be opening to the right. I shouldn't intersect the directrix. I want to be opening down so that the bowl is eating up the focus and the directrix is outside. And what do you guys know? You have that symmetry, right? That the distance from the vertex to the focus, vertex to the directrix is the same. So if I have a total of 8 units here, or you can think of it as 2p if you want, then I need to divide it in half. And so my p-value is 4. That means that my vertex is going to be living over 0 and up 4 units. So that allows me to sort of visualize the information and think about how to create this function. It's opening down, so once again, I'll have x minus h quantity squared, and I'll have my 4p times y minus k. Let's go ahead and plug in what we just found. Our h is 0, 4, so we're going to have x squared, right? I don't have to write minus 0. If you did, it's no big deal. It's opening down, so I said p was 4, but since I'm opening down, I want to use -4. Right? P equals -4, so that's -16 y minus 4, this 4 coming from the vertex that I found with the midpoint. And that is the equation for that particular parabola in conic form. You've really got to try them out though. I know you've done them before, but it's been a while. So work through them, make sure that you're comfortable converting from this form to the standard form, that you understand how to graph these and what's included. And then these ones tend to go a little bit quicker finding the equation, but there's again a lot of ways that they can ask the same question. So you're going to want to work through them. So there's your suggested assignment. Use this time for the rest of the hour to work on that. Come in with questions tomorrow because tomorrow we're going to do applications and story problems that involve our parabolas.